Okay, so we're still looking at drawing Lewis structures, and now we're going to look at a couple where some things you have to look out for. So some kind of like oddities, and there's always usually a couple oddities in chemistry. So these are the oddities for Lewis structures. Again, Lewis structures aren't that bad. You just need to make sure that you're looking and are aware for these. So the first ones that we're going to look at are when there are some elements that have less than an octet. And if you have less than an octet, then you're called electron deficient because you do not have the 8 electrons that you normally should. So you know that all elements want to have 8 electrons, but in certain situations, forming a bond is still better than not forming a bond, even if you don't get 8. So just two that you really need to be aware of. Boron and beryllium really tend to be electron deficient. Sometimes beryllium will only take 4 electrons instead of the normal 8. So if we look here, we have boron trifluoride. We have our need. Let me just move this so we can actually see. Equals 4 times 8, so we need 32 electrons available. If you look boron up, he's in the third tall column over, which means he has 3 valence electrons. And we have 3 fluorines. They're halogen, so that's 7 electrons each. So we have 24 electrons. And that means that we are going to share 8, which means that we need 4 bonds. Now, with any other situation, this would be fine and that'd be great. The problem is if you think of what you're going to have here, what we have is we're basically going to have boron in the middle, because he's the least electronegative, and then we have 3 fluorines that need to bond. And you kind of have to keep this in mind when you're doing this. Like, what is it actually going to look like? And I'm just kind of drawing them in a triangle for no reason at this moment, but just so we have them. So if we are going to put 4 bonds on this, what we're going to need is we would need a double bond on one of the fluorines. And one of the rules of bonding is that fluorine will not form double or triple bonds. He's the most electronegative element, and he will not allow this. So you may want to give yourself like a little note. Fluorine will not form double or triple bonds. So what happens is basically fluorine kind of gives an ultimatum and says, okay, boron, I will bond with you, but I'm not going to do double bonds. So what happens here is you actually need to change this need available share. So you may want to make yourself, you can make a note or whatever, but due to fluorine not willing to do a double bond, what happens is boron says, okay, I will not take 8. And what happens is the 3 fluorines still want 8. And what boron says is I'll only take 6. So what happens is instead of needing 32 electrons, we only need 30. The available is still the same. The share is only 6, which means that we only need 3 bonds. And what that allows to do is it allows everyone to get an octet except for boron. But it's something that boron, in this case, it's better for boron to actually bond to fluorine, even if it only gets 6, than being by itself. There's more about this in your book. You should read your book. And then make sure you go back and make sure everyone has access to 8 except for boron. And now what you have to be really careful of is you need to make sure that you're only using 24 electrons. Because if you're not careful and you're not counting your electrons, then what happens is you end up giving boron the octet, and he's not allowed to have it. Because if you count 2, 4, 6, blah, 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 that is 24 electrons. So you have no more to give boron. So just make sure you can never give your Lewis structures more or less than how many are available. So just kind of like double check that before you move on. The other situation where they're a little different is when you have more than an octet. So this is called hypervalence or an expanded valence shell. These are pretty easy to tell because there will be an indication, and we'll highlight the indication of it. But I'll tell you, just for your own personal things, there are elements that tend to do it. Sulfur is probably the most common. Phosphorus, arsenic, antimony, bromine, iodine, and xenon. But you may want to note there can be others. So these are the most common ones that can do this. Again, I don't think you need to memorize them. I just think you need to be aware of it. And then this is a big thing that you want to highlight, underline, make sure you know. They only do it when they need to. So it's not like they want more than 8. It's not like they're like electron happy. It's just that they only do it if it's a necessity. Like if there's just too many of something, these are the guys that like step up and say, it's okay, I'll do it. It's kind of like when you're in a group and the other people aren't doing anything, you're like, fine, I'll do the extra work. So these are the guys that do that. So if we look at sulfur hexafluoride, we'll do our need available share. So our need is we have 5 things and they all need 8 electrons. So we need 40 electrons available. Sulfur has 6 and we have 4 fluorines and they each have 7. So we have 34. And then our share, so we do 40 minus 36. That's 6 electrons, which means 3 bonds. And then this is where you want to make the thing. This indicates hypervalence. And the reason it indicates hypervalence is there are less bonds needed than we must use to connect the elements. So what I mean by that is if we draw it, we know sulfur's in the middle. I need 1 for fluorine, and I need a bond for each fluorine. So it says there's sulfur with 4 fluorines, so I have to have 4 bonds because I have to bond sulfur to fluorine. And again, they're just going to be like single bonds off of it. The problem here is we need 4 bonds. It's an absolute necessity, but this is telling us we only need 3. And it's not that you did anything wrong. It's not that, oh my God, the world is ending. It just means that you have to make sure that you actually check this. So what this means is when we put in all our electrons, there's going to be extra electrons left over. So you may want to mark that. This means there will be extra electrons at the end, and they go on the central atom. So what we do is we have it made. We add all our extra dots in so that they can have their octet. And then you count them all up. So I count up how many electrons I have right now. I only am using 32. And remember, the magic number is your available. I really have 34. I have 2 extra electrons. And that means they are going to go on the sulfur. And a lot of times when you do hypervalence, you kind of draw a little circle around it to try and show that, hey, it really is on that sulfur. You don't have to, but you can if you want. Oh, sorry. So just be aware of this. They do this on the AP test. I will do this to you. They will definitely do it to you in college. These aren't freak things. These are just unusual things. And you need to be aware that not everything is always the simplest, route. So just make sure you're paying attention to those. The only other thing I just want to show you real quick is resonance. So this is another thing that you have to watch out for. So resonance is something that you need to be aware of. And when something has resonance, it's like I can draw it. Like if I drew it and someone else in the classroom drew it, we could draw it our own way, and there's more than one right way to draw it. So there's two examples here. The first one here is ozone, and you can see there's two different ways to draw it. And basically what we're saying is should the double bond be on the left or should the double bond be on the right? And this is after doing need available share and you're drawing everything. It's just like you may draw one and your partner may draw it slightly different. So the answer with resonance is there's really not either of these two. What happens is it's kind of stuck in the middle of these. So what happens is you don't have to draw this, but you need to understand it. And your book explains it really well. What it really looks like is you have your oxygens. So let me just draw them. And then instead of having one side have a double and the other side have a single, what you kind of have is like a 1.5 bond. And you know it's like a 1.5 bond because you have two different possibilities. So you have a double bond split between them. So you know both sides have a single bond, and then the extra bond is kind of split between the two. So what resonance tries to show is that smearing of electrons. And this bond is stronger than a single bond and weaker than a double bond. Down here is nitrate, the anion, which you should all know is NO3 minus 1. And you can see this one has three possibilities. So when you draw this one, and again I have to draw it at the bottom here, so I apologize. We have our oxygen. Sorry, that's really little. You have to have your single bonds because they're not going anywhere. And then this one, because it's smeared between three different areas, it's like a 1 1/3 bond. So it's stronger than a single bond, but it's not really any of them. If there is something that has this ability where realistically, why is this oxygen any more special than this oxygen or this oxygen, you need to indicate there's resonance and you need to draw the resonance. And you need to practice being aware of when there is resonance and when there's not resonance. So just make sure you're looking into it. And then the last thing for this section is just benzene is kind of the king of the resonance. So you can see you can either go like the doubles at the top or the double bond can be at the bottom. But there's two possibilities. You can draw it full out. You can draw it the shortcut way. You can draw it benzene like this. And then this is where it's trying to show you in here that it's not really any of them. You can see that it's smeared the whole way around. And benzene is like freakishly strong and freakishly stable because of this resonance. So this is a really important part of the chapter. It's something you have to understand. It's something they frequently ask you on the AP test and in college. So you don't want to go out of here whether you think you're going to take the AP test or not. You want to have an understanding of this because it's very important for organic chemistry. It's important for a lot of engineering applications. So just make sure you get this part of it.